Yeah, so I'm very, very delighted to be here. This has been a terrifically delightful month to spend here at visiting KAIST. I'm kind of marveling at just how quickly it's gone. It seems like I just got here, but sadly I have to go home, where there's a whole lot of work waiting for me. But anyway. So today I'm going to talk about a big project that I've worked on for really many years, and it's just completed a little over a year ago now. It's on what I'm calling very small product sets. So here's the setup. Pretty simple. I'm going to have a group G. So G is always going to be a group. A and B are always going to be subsets of that group that are finite and non-empty. And I'm going to be interested in this set that I call the sum set, A plus B. So the set of all elements that you can express as something in A plus something in B. And in this framework, there are a couple of very prominent questions that we're going to be interested in. The first is just how small can that sum set be? And second, if it is small, then why? So more precisely, if this sum set is fairly small, say relative to our known lower bounds, we'd like to say something about the structure of A and B, and conceivably even something about the structure of G. Now for my purposes, I'm going to be focusing on what I'm going to call very small sum sets. And here's the definition. A sum set is very small if the size of the sum set is smaller than the sum of the sizes. Now, if you think about this, this is extreme, right? I mean, if A and B both have n elements, then there are n squared possible combinations that you could get. And I'm going to be focusing on the case where the size of that sum would be smaller than 2n. Right? So this is a very extreme case. In fact, this is kind of the most extreme case that I think we have a chance of really characterizing precisely. So I'm not going to go into this at any great length, but this realm here of very small is a realm in which we're going to see sort of precise answers. We're going to get a good understanding of how this can possibly happen. There's a lot of very serious work that's done in the realm, not where A plus B is very small, but maybe where the size of A plus B is at most a constant times size of A plus size of B. So maybe you consider this inequality with a factor of 10, and then you probably can't hope for a precise answer, but you might hope for a rough one. And indeed, there are some very strong theorems. Notably, there's a very powerful theorem due to Brouillard and Green and Tau, which tells you something roughly about the structure of a set A when A plus A has size only a constant times the size of A. And in fact, they can do that in general groups under certain assumptions. Now, anyway, so there's a whole lot of very powerful mathematics concerned with understanding the structure of A and B when they have small sum set. As I say, I'm going to focus on this very small case, and this is a case when the problem is really very combinatorial. One more little addendum here. Sometimes I'm going to use multiplicative notation. So those of you who have been sitting in on my additive combinatorics seminar know that I sort of move back and forth between the two, and let me apologize in advance that I'll be doing a little bit of that in this talk as well. I mean, the reason is that some of the groups that we'll be working with will be things like the integers and the integers mod p, where we want to use addition. I'm interested in the additive groups there. But in cases when we're working with an arbitrary multiplicative group, it seems a little nicer to write using multiplicative notation when the operation's not commutative, and that's also the convention of the subject. Anyway, so but everything's all the same. So if you're writing the thing multiplicatively, then you're interested in this set here that I call the product set, and it's going to be very small. Same thing if that size of this product set is smaller than the sum of the sizes. Okay. So what we're going to do, I'm going to kind of step through talking about this. Let me go back. Right. So I'm going to kind of step through here talking about these two central questions in various groups. So first we're going to think about when the group is the integers, and then the integers modulo a prime, and then an arbitrary abelian group, and then a non-abelian group. And we're not going to see too many proofs here, but for the first case, when the group is the integers, then the situation's pretty easy, and I can indicate it fairly quickly. So I claim that if you take two finite non-empty subsets of integers, then the size of the sum set is always at least the sum of the sizes minus 1. And that's not too hard. The thing we take advantage of is the fact that the integers have a total order on them. Right? So my elements in A, I've ordered here A1 up to AM, and the elements in B are ordered B1 up to Bn. If you do that, it's very easy to identify some distinct elements in this sum set. So the sum set is going to contain A1 plus B1, and also A2 plus B1, and A3 plus B1, and so on. And you can tell these things are different, right? Because A2 is bigger than A1, so these two elements, this element is really bigger than that one, and so on. I can keep increasing the index of that A term up to here, and then I can increase the sequence of the B's. And that brings me up to here, and this is m plus n minus 1 distinct elements. Right? So my sum set is always guaranteed to have at least this size. I'm not going to do this precisely, but you can you can imagine this process in a little bit more generality, starting with A1 plus B1 and moving to AM plus Bn, or AM plus Bn. But now you don't just have, you could instead of just incrementing the index of A each time and then B, you could kind of alternate. So each time I'm going to start here and take a step by either incrementing the index of the A or the B. And I've drawn a picture for you here. So here I've put the A's on the horizontal and B's on the vertical. And so these points sort of correspond to the possible combinations of A's and B's. And however you'd transverse this, starting in the lower left and going to the right and up, you have to see distinct elements. And each of these gets you that bound of m plus n minus 1. And with a little bit of work here, so in fact, sorry, what am I getting to? So if you were hoping that your sum set had size exactly m plus n minus 1, right? If you were hoping that it was going to hit that lower bound, then all of these possible sequences of elements you would see would have to be the same. And if you think about this a little bit, it will tell you the following. If you have two subsets of integers that are finite and unempty, and the subset is very small, meaning size of A plus B is less than the sum of the sizes. Right? We know it can only be one less than the sum of the sizes. So if it's very small, you only missed by one. And if that happens, then you have to have one of the following two conclusions. Either one of the sets had size 1. That obviously can happen, right? If one of the sets has size 1, then the size of the sum set is just the size of the other set. And so then you're going to have a very small sum set. The other possibility is that I give you two arithmetic progressions with a common difference. So that's sort of the richer, more interesting structure, right? If I take A to be 0 up to 10, and B to be 0 up to 20, then when I add them, I get 0 up to 30. So I've added a set of size 11 and a set of size 21, and I've got a set of size 31, which is one less than the sum of the sizes. Okay, so for the integers, this game is pretty simple. So again, if I give you two sets of integers, the sum set will have size at least the sum of the sizes minus 1, and the only way you can hit that, the only way you can be very small is either taking one of the two sets to be size 1 or both to be arithmetic progressions. Okay, Now I want to move to the group of integers modulo a prime, and so here P is a prime number, and A and B are again non-empty subsets. Now it would be foolish to hope that the size of the sum set was always at least the sum of the sizes, because I could feed in A and B both being the entire group. Right? I'm allowed for A and B to both equal this entire group, and then the size of the sum set is just going to be B again. It's just going to be the whole group. So here there's a new conclusion here, a new reason why you might have a small sum set. Maybe the A plus B is the whole group. And in fact, what Cauchy and Davenport's theorem says is that, in fact, either you get this same nice bound that we had in the integers, or the reason you don't is that we filled out, we got the entire group. All right, so it's a very pleasing alternative. Again, you're sort of either getting this sum of the sizes -1, or you're getting the whole group. Now the characterization problem of determining the small sum sets gets considerably more difficult. So this was solved in the 40s by Vosper, who proved I guess I haven't written this properly, but Vosper has proved a theorem which characterizes what all very small sum sets look like in this group. And again, his theorem is going to look, it starts off looking exactly like the small sum sets we saw in the integers. One possibility, one way to construct a very small sum set in this group would be to take one of your sets to be size 1. Another thing you could do is take both to be arithmetic progressions with a common difference. I mean, that still makes perfect sense in this setting, right? You take 0 and G and 2G and 3G and 4G, and you do something similar for B, and then when you add them up, the sum of the sizes is one less. There also is another outcome here associated with the possibility that the size of this sum set is either the whole group or is very close to it. So it could be that the size of the sum set is everything, or it could be that the sum set is all but one element, and that's another possible outcome. Okay, so again, in the big picture here, the natural lower bound for the integers we saw is size of A plus size of B minus 1. It's very easy to characterize the small sum sets. In this group of integers modulo a prime, we've got the Cauchy-Davenport theorem, which gives us a natural analog of that easy theorem for the integers, and Vosper's characterized the very small sum sets. Now for abelian groups, Martin Kneser found a natural lower bound on the size of a sum set that gives a generalization of Cauchy-Davenport. And his theorem says, so now G is any abelian group, and again, A and B are going to be finite non-empty subsets, then here's what you get. You always find a subgroup H of the group so that the size of the sum set of A plus B is at least the size of A plus the size of B minus the order of that subgroup H. And moreover, if you take A plus B and add to it anything in that subgroup H, you're still in that sum set A plus B. So let's verify that this implies Cauchy-Davenport. So if my group here was just the integers modulo a prime, well then I don't have very many choices for the subgroup. Right? The subgroup can either be trivial or it can be the whole group. So if you get the trivial subgroup, then the size of A plus B is at least size of A plus size of B minus 1. And that's one of the happy conclusions. Right? So if we apply this in the case when the group is the integers modulo a prime and this subgroup H comes out trivial, then we have the first bound that we want, namely the size of the sum set is at least sum of the sizes minus 1. If, on the other hand, H was the whole group, well, then this conclusion tells us that, in fact, A plus B has to be the whole group. Right? So Kneser's theorem is a natural generalization of Cauchy-Davenport. And now, again, we can look to this same problem of these very small sum sets. Right? So we have kind of a natural lower bound on the size of a sum set. And it's sort of telling us that the size of the sum set should usually be at least the size of A plus B. Right? It should sort of be this case when, like, we're going to be interested in the case when, the very small case is when the size of this sum set is strictly less than size of A plus size of B. Right? So we lose this term. But that's sort of the interesting realm here. Those are the tight cases here. And in fact, Kemperman succeeded. So Kemperman proved a rather technical theorem that gives a description of all very small sum sets in abelian groups. Okay, so now on to non-abelian. So for non-abelian, or arbitrary groups. So for non-abelian, I have a theorem which generalizes Kneser's theorem. So here A and B, again, just finite non-empty subsets. I've switched to multiplicative notation. So I'm thinking about non-abelian groups, so we'll use multiplicative notation now. And what happens is there always exists a subgroup H satisfying these two conclusions. So the first one says the size of the product set is at least the size of A plus the size of B minus the size of H. So that looks exactly as it did in the abelian case. The second condition is rather more complicated. It says for any element of the product set, there exists some element Y in the group, so that when you take X, this element of the product set given by X, and multiply by a suitable conjugate of H, you stay inside the product set. In the case when your group was actually abelian, of course, YHY inverse is the same as H. And so this says for every element in the product set, when you multiply it by H, you stay inside the product set. And so that just lines up with, that lines up with, oh, now I'm going to go the wrong way. So that lines up with this condition here when the group is abelian. But it works in general. I like this theorem. It took lots of work, but it's actually kind of not the point. In fact, the program here is very different. It breaks the mold of the earlier cases. So the program here is, what we do is we just classify all the very small product sets. So I'm going to prove that classification theorem. And then once I have the classification theorem, I'm just going to kind of read this off. Right? So whereas for both Cauchy-Davenport and Kneser, you sort of first establish these natural lower bounds, and then you work out what these very small sum sets look like, sort of really leaning very heavily on the existing lower bound. Here we have to do something, or here I ended up doing something completely different. Namely, I ended up just figuring out what every single very small product set looks like, and then reading this theorem off. Well, this is an enormously complicated theorem. I mean, the statement of what these very small product sets actually look like, I mean, it's appearing on like page 40 of the paper, right? I mean, it's a very, very complicated kind of recursive thing, and I'm not gonna go into it. But I'd like to give you some idea how the argument goes, and we'll see some of the structures. So I mean, it's like there are a lot of terrible technical details, but there are some useful things that I can say that give an indication of where this thing comes from. And in fact, what I'm going to do now is I'm going to jump back to that Cauchy-Davenport theorem, and I'm going to give you a proof of Cauchy-Davenport that's not really the standard one. It's using a kind of a different transform than is commonly adopted. But the point of this one is that it generalizes a little better, and in particular, it's going to work in a non-abelian setting. Okay. So first I'm going to need one simple definition, that of shifting. If I give you some group element in a set C, we've already defined what it means to add the singleton group element G to C, but I'm just going to drop the braces for brevity, and I'll do that on either side, and we call those shifts of the set C. I'll think about taking C and just shifting every element by adding G. Okay. Now what I've written up here is the key property that's going to kind of underlie this particular proof. And so for those of you who were taking my, following my lecture series, this is a different proof now. So I'm doing a trickier transform for the reason that it's going to generalize better. Anyway, so what I'm claiming is if you take A and shift it by adding G and then intersect it with A, and then add that to the set that you get by taking B and unioning it with the shift by minus G, that's still a subset of A plus B. Now, once again, this is going to be very easy to verify. So, well, let's consider a pair of elements, x from this term and y from this term. Well, y is from this union of two sets. So y has to come either from this b or from minus g plus b. Suppose y comes from b. Well, in that case, you're in a good shape, right? Because x lives in the set A, right? X has to be in both of these. So x lives in A, and that means you see the sum x plus y over here. The other possibility is that y might come from minus g plus b. If y is from minus g plus b, well, you could probably guess. Well, now x has the form a plus g, right? So if x has the form a plus g and y is the form minus g plus b, then x plus y is still going to appear in this sum set over here, right? So I can do this sort of funny operation where I take A and intersect it with a shift by plus g, and B and union it with a shift by minus g, and I'm still trapped. I still have a subset of my original sum set. Here's another variant that follows from the same exact argument. You could, instead of doing the intersection here and the union here, you could flip those. You could do the union over here and the intersection here. And same reasoning, you're still going to be a subset of that A plus B sum set. Now what's the point of all this? Well, let's look at the thing we're aiming to prove. I'm aiming to prove that the size of the sum set is at least this quantity where you see the sum of the sizes appearing over here. So I'm really interested in kind of comparing the size of the sum set with the sum of the sizes. Right? So if I started with this original pair A and B, I'm now giving you two new pairs, this pair of elements and this pair of elements. And I know that the size of this sum set, it can only go down, and the size of this sum set can only go down. How about the size of the sum ends? How about the sizes of these four sets? Well, I don't really know what the size of this set is. I mean, it could be lots of different things. But I know that the size of this set plus the size of this set is twice the size of A, right? The size of A and the size of A plus G is the same as the size of A. So if I take the intersection of these two together with their union, I'm just getting the sum of the sizes of these two will be twice the size of A. Same over here, the sum of the sizes of these two is twice the size of B. Right? So I kind of started with a pair, and if you're interested in the size of the sum set compared to the sum of the sizes, you can see that the average sum of the sizes of A and B over these two, it's only going, I mean, it's the same as the size of A plus the size of B. Right? So the sort of average size over these two pairs is the same as the original sum of the sizes of the sets, and the sizes of both sum sets are only going down. And that's the key thing we're going to take advantage of. So let's consider. So I'm going to now give the proof. It's going to be based on that. I'll do my best to sort of say this kind of compactly. So, So our counterexample, so I'm going to proceed by choosing a minimal counterexample in some sense, and then I'll proceed toward a contradiction. So I'm going to suppose that this theorem is false and choose a counterexample, choose some pair A, B, for which this quantity is maximum. So the size of the sum of the sizes of the sets minus the size of A plus B is maximum. And subject to that, the size of A is minimum. Right? So if you could find some pair where the size of the sum set was much smaller than the sum of the sizes, that would be great. That's my first criterion, is to make the difference between the size of the sum of the sizes and the size of the sum set big in this sense. And my second priority is to make A small. Now it's pretty easy to see that since our pair is a counterexample, A is not a singleton, because this theorem is obviously true for singletons. A is also not the whole group. Same thing, the theorem obviously holds for that case. So I can assume A is not everything. Since A is not everything, it has at least two distinct elements, and that means I could choose a shift that carries one to the other, a non-zero shift. And if you look, that element G that you shift by will satisfy this property, right? When you take A and intersect it by A plus G, what you get is non-empty. And that's sort of the key here. Now we're going to take advantage of this fact. It's also easy to observe that A intersect A plus G is not everything. I mean, if with a group of integers modulo prime, it's just generated by that element G, right? So you can imagine starting at 0, then G, then 2G, and so on all around. If A has the property that when you take A and you shift it by G, you get A again, then anytime you have an element, you have to have the next one in the cyclic order. So you'd have to have the whole group. So this set that we've constructed here has this property that A intersect A plus G is not empty, and it's not all of A. And now what you do is you just consider those two new sum sets that we got. And I'm not going to say this in gory detail, but the point is that the sum of the sizes of these four sets is twice the size of A plus twice the size of B. And each of these new sum sets can only get smaller. And the upshot of that is that either one of these two new pairs you've got is more extreme relative to my first criterion, or they're both tied relative to the first criterion with the original, but then this first one is actually still better because it wins according to the second condition. So this kind of transform is sort of what makes it all go. And if we just sort of choose a very careful counterexample, then we, just using that transform, we're going to be able to construct a new pair, either this pair or this pair, that's just better relative to our ordering. And that contradiction completes the proof. Okay, so there's a slightly funny proof of Cauchy-Davenport. Part of the point of this is that this argument still works in a non-abelian setting. So this kind of general technique of taking your pair of sets A and B and replacing them with either this kind of intersection in this union or the reverse of that still makes sense. So once again, you can see I've sort of cavalierly switched to multiplicative notation. I hope that isn't bothering you. Again, you can readily identify these identities, and this makes sense in a non-commutative setting. We're going to take advantage of that. Now, another ingredient in the general proof here is this third set, Z. So you have your group G. I'm now assuming that I'm going to be thinking about non-abelian groups now. So I'll be working multiplicatively. And now for simplicity, I'm going to be assuming that G is finite. That's not a serious restriction. In the actual event, you can allow G to be infinite, and then C ends up being a cofinite set. But to avoid saying cofinite all the time, it's just easier for the exposition to work with finite groups. So G is a finite multiplicative group, and I've given you this very small product set, and I'm defining C to be this set. It's G, it's the complement of all those things that are the inverse of something in A times B. What's the point? Just by construction, 1 is not in the triple product ABC. Right? I chose C precisely to be all those elements that have the property that they're not the inverse of something in A times B. Right? So 1 will not be in the triple product ABC. Now, by assumption, AB was very small. And that tells me something about C, right? The size of A plus the size of B plus the size of C. Well, the size of C is the size of the whole group minus the size of the product set. And by assumption, the size of the product set was smaller than the sum of the sizes. So what I've got is 3 sets here where the sum of their sizes is larger than the order of the group. Now, in fact, there's a kind of added symmetry to the problem here. In fact, if I give you a triple that satisfies these 2 properties, or I mean, even just starting from here, I can conclude that B times C is very small. And the point is that this set, B times C, that new product set, it still has to be disjoint from A inverse. Right? I know that 1 does not appear in the triple product, so BC has to be disjoint from A inverse. So the size of BC is at most the size of G minus the size of A inverse, and that's less than the size of B plus the size of C. So in fact, anytime I'm giving you this kind of very small product set between A and B, if you construct C in this fashion, then you learn that BC is very small, and similarly CA is very small. So you actually get sort of 3 small product sets. And that's worth a definition. So I'm going to define a triple ABC of subsets to be a trio if 1 is not in that triple product. And I mean, you might look at this line and think it looks funny, but well, whatever. We're going to call this product set, this trio, very small if the sum of the sizes is more than the order of the group. Yeah, admittedly, that's sounding a little strange now, but well, so be it. Okay. Oh, I should. Well, everything I've presented to you up until now was known in 1950, basically. I mean, all of these sort of ideas that we've seen are classical, and people have looked at these things over and over and played some of these little intersection union games. And the new thing that I'm going to bring to this is graphs. So I'm a graph theorist, so it's kind of only right. What I'm going to do now is I'm going to start with that sort of trio, ABC, and use it to construct an exceptional graph. And here we go. So here's what I'm going to do. I'm going to take 3 copies of my group G. So this is going to be a so-called tripartite graph. So I've got three sets of vertices here, 1, 2, 3, and all of the edges go between these different blocks. I'm going to call them blocks. I've got 3 blocks here, and all the edges go between these ones. I've sort of drawn a little arrowhead here and written a dot A. What does that mean? That means that the rule for when you have an edge between 2 elements here is the following. You have an edge between, say, an element x in here and y in here if you can get from x to y by right multiplying by something in the set A. Okay, so that's the rule for when 2 of these are adjacent. And same thing dot B and same thing dot C. So I'm going to think about this as being an undirected graph. I don't really want those arrowheads on my edges in the end, but the arrowhead is necessary here for the definition. Right, so this just tells me adjacency here. And let's read off what properties it has now. First key property is that this graph has no triangle. Right? If you think about what it would mean to have a triangle, you'd have to start at an element, say x, and multiply on the right by something in A, multiply on the right by something in B, multiply on the right by something in C, and then get back to x. Well, then you'd have to have 1 in the triple product ABC. So the graph I've constructed doesn't have any triangle. Now, assuming that I had this very small property, then in fact you have lots of edges between these blocks. So, but for each of these blocks that you see here, you have a bipartite graph between. You have a bipartite graph here, and we can compute the density of that, the edge density of that bipartite graph. And by that I mean just the total number of edges that are present divided by the total number that would be possible. In this case, that's very easy to compute. Each vertex here is going to be joined to size of A vertices over here. And so the density of this bipartite graph is going to be the size of A divided by the size of G. The density of this bipartite graph is the size of B divided by the size of G, size of C divided by the size of G. So when you take this graph and you sum up the densities of these three bipartite graphs, you're going to get something more than 1, assuming now that we started with this sort of very small property. The last property we have is that our group has a natural action on this. If you were to imagine taking your favorite group element, G, and you left multiply everything in here by that G, and everything in here by that G, and everything in here by that G, that's going to give an automorphism of this graph. Right? That's going to permute these vertices about, and permute these vertices about, and permute these about. But since my multiplication here, my adjacency is defined in terms of right multiplication, and my group will act naturally on the left. If you multiply this on the left by G and this on the left by G, you aren't going to change this adjacency rule. So again, I've sort of taken my triple of sets here, and I'm constructing a funny graph that has a couple of exceptional properties. It has no triangle, it has a lot of edges, the sum of these densities is large, and it has a lot of symmetry. It has this nice symmetry. Your group acts on these on this graph in a way that's transitive on each of these blocks. And now what we're going to do is just try to forget groups completely and think about graphs. So now I'm going to, forget groups. Let's just think about graphs. So let's think about tripartite graphs which have these properties. They're going to have no triangle. The sum of the densities of those three bipartite subgraphs is more than 1. And it has the same symmetry property. So the subgroup of the automorphism group, which you have to, when I'm looking at the group acting, no fair interchanging these two blocks. I'm only interested in the automorphisms of the graph that fix each of these three blocks. So I want that subgroup of the automorphism group which fixes each block as a set. It should still act transitively. Right, so this is just a completely new problem. So I want to forget groups. I want to just think about these tripartite graphs that have this no triangle condition, and this density condition, and this symmetry condition. And this is really what, this is, well, it's not maybe the only thing, but it's maybe the biggest thing that I'm doing differently than what anybody else was doing before me. What's happened here is, effectively, we've moved from the world of groups to group actions. Right? So instead of trying to focus on subsets of groups, I'm now focusing on this graph structure, on this natural kind of extremal structure on which I have a nice group action. And that's a powerful move. And we'll see a couple reasons why. But first I want to give you an example. So I want to sort of break you out of thinking of these things as always constructed in the most naive way. So suppose you have a finite map on a surface. So it's got vertices, edges, and faces. And I'm going to assume that the automorphism group, so the symmetry group, acts transitively on vertices, edges, and faces. So we've got something like, so I've got a dodecahedron on a sphere here. Right? And I've got, if you think about the rotations of this, they're going to act transitively on the vertices and the edges and the faces. Right? You can think of a rotation that takes any one vertex to any other, and same with a pair of edges or faces. And now I'm going to use this to construct one of my objects. And here's the rule. So now my three sets are going to be the vertices and edges and faces of this map. And my rule for when two vertices of this graph are joined by an edge is going to be based on the incidence properties of that map. And here it is. So I'm going to declare one of these vertices corresponding to an edge to be adjacent to one of these vertices corresponding to a face if that edge and that face are incident in my map. And same thing, I'll use incidence over here. So one of my vertices is going to be incident with one of my edges if, there's so many, this gets messy because there are too many things being called vertices at the moment. One of these guys is going to be adjacent to one of these guys if this vertex is incident with this edge in my map. Only down here what I've done is I've used the flip, non-adjacency. So a vertex, one of these guys is going to be, so you'll have an edge between this vertex and this face if this vertex and that face are non-incident in the map. And you can see that this does guarantee me something that's triangle free. If you have, suppose you have a vertex that's incident with some edge and that edge is incident with a face, that can only happen in a very simple way, right? So if you have, it's just a map on a surface, right? So if you have a vertex that's incident with an edge and this edge is incident with a face, then that vertex will as well be incident with the face. So the way I've constructed my graph here, I've guaranteed that there's going to be no triangle. Another property that we naturally have just from my assumptions and my construction is that the automorphism group of the map, like we can think of all those automorphisms of this map on the sphere, say, those things act nicely on my graph, right? So those automorphisms of the map, they act transitively on the vertices and faces and edges, and they can carry any vertex to any other, and any edge to any other, and any face to any other. Okay, so now I'm going to compute the densities here, and I'm maybe going to fast forward this just in the interest of time. So when you go to compute the densities here, computing the density of these two guys is pretty easy, because each edge is only incident with two vertices, right? So each edge is incident with two out of the total number, which I'm denoting as little v, of vertices. Same thing, each edge is incident with just two faces. So the density of this bipartite graph is 2 over the number of faces. The density here is a little bit trickier to compute, but it's actually, well, let me just say it. It's really easy. I'm just going to draw the same picture again. I mean, anytime you have a vertex that's incident with a face, right? So here's a vertex that's incident with this face. There are actually two edges that we could think of as being in between the vertex and the face, right? There are two edges that are incident with both that vertex and that face. Now every edge, if you focus on an edge, this edge is going to sit in between this vertex and this face, and this vertex and this face, and this vertex and this face, and this vertex and this face. So each edge here sits in between 4 different vertex face pairs, and each vertex face pair has two edges in between. So to count the number of incident vertices and faces, right? So each edge gives me 4 pairs, but each one gets counted twice. So the number of vertex face incidences is equal to twice the number of edges. So the density of the graph of vertex face incidences, so if I take the vertex face incidence graph, the density of that will be 2e, the number of incidences, divided by vf, which is the total number possible. And if I were to take the non-incidence graph here, well, its density is 1 minus that. So the density of this one's 1 minus 2e over vf. And so now I'm interested in when these three things could possibly sum up to be more than 1. Well, when is that? Well, when you sum up these densities, here it is written out. I've got 2 over f plus 1 minus 2e over vf plus 1 over 2v. Well, that's the same as 1 plus 2 over vf times this strange quantity. Well, it's not all that strange. It's a quantity you've seen before, right? That's the Euler characteristic. So what this is telling us is that our density condition, our sum of the densities, is going to be more than 1 precisely when the Euler characteristic is positive. So in fact, the structure that I've created here, it's going to have my triangle free property. It's going to have the symmetry property that we desire. The density condition is going to be satisfied precisely when I had a map that was on a surface of positive Euler characteristic. And in fact, those maps, those things do appear. So they're going to be kind of sporadic things. Like right now I'm sort of lost in the midst of trying to give you some hint of this massive structure theorem. So the theorem is going to tell us that anytime you have this very small product set in an arbitrary group, then it has one of a certain number of forms. And what the structure theorem looks like is that there are certain infinite families, and then there are some sporadic ones that appear. And in fact, these guys are the main source of the sporadic ones. So these guys are going to give rise to some sporadic examples of small product sets. Now, in fact, I was advertising the great joy of graphs here, and I feel that very strongly. But it's important to understand how we can go back and forth. And in fact, anytime you have one of my structures, you can actually back it up and construct a small product set in a suitable group. And I'm not going to say this very precisely. I'll say what the right analogy is. So if you've sort of seen the thing I'm thinking of, you could complete it in this case. So so I'm talking about regular action, right? So I always have a group G acting on some set, which I'll just call S. And if you think about so S here could be X or Y or Z. And I'm always insisting that group have a transitive action. And what that means is that for any 2 points in S, there's some group element that sends one to the other. So for all X and Y in S, there exists some group element such that when you apply G to X, you get Y. A regular action means there's exactly one. So I could say it's regular for any 2 points in S, there is exactly one group element that sends one to the other. So if you have a group acting regularly on a set, then there's a very natural way of taking that set and associating it with the group. And the idea is simple. If the group is acting on your set, you just choose some base point. So sorry, I want to assume regular action. So I want to have a group acting regularly on a set. So what that means is that for any 2 elements in the set, there's a unique group element that carries one to the other. And in that case, there's a simple way of associating these guys with group elements. Namely, you choose a base point, and then you for any for any point in this set, you assign it to the unique group element that carries the base point there. Right? So that gives you a natural correspondence between the elements of this set and the group. So if your group was acting regularly, you can really just think about those elements in the set as actually being group elements. And and when that happens in this setting, if these sets X and Y and Z, if they all had the same size as the group and the group was acting regularly, you can just use that mapping and build me a small product set. And in fact, in general, you can do something similar. So instead of associating this element of the set with the single group element that mapped your base point here, you associate it with the set of group elements. And that assigns cosets to your elements in your set. And in fact, you can kind of build something similar. So I'm not going to say this terribly precisely. I did. Not really. I built this yesterday, so I feel like I ought to card it out. So this is a cube, right? The rotational symmetry group of a cube is S4, and there's an easy way to see it. It's S4 on the 4 diagonals. So you see I've colored the 4 diagonals with different colors, and each permutation of those 4 colors corresponds uniquely to a rotation of the cube. So if you take these 2 edges and flip them, you'll see that I'm transposing the green and the yellow. And if you look at it more like this, you'll see that I'm not actually, that red and blue are both staying fixed, right? So this particular automorphism is a transposition, right? Now the fact that we have S4 acting naturally on our cube is going to allow us to take this structure, this idea of Sabadushi's, together with this structure, this vertex edge face structure, and actually construct an exceptional product set that occurs only in the group S4. And the only thing you needed here was that S4 had this nice action on the cube that's transitive on the vertices and edges and on the faces. In fact, there are some other subgroups of the cube there are some other groups that do similarly, and in those groups you also get these exceptional product sets. Okay, so so I'm let me sort of try and finish up here. So the proof. This is a horrible thing. I mean, you should never. You're actually. I've written this in such a way that all the technical details are pushed kind of late in the paper, so you can get the idea of the proof early on. But heaven help my referee. This structure theorem is very, very complicated. I mean, just the statement of it is quite terrible. But the gist of it is that you have a few types of recursive structures and some infinite families of structures. But the main ones are things that we saw before. There are cases where kind of one of the sets is small, or you have something that's like an arithmetic progression. I mean, those are really still the 2 defining things that we see. And it basically breaks up into some sensible infinite families plus a few sporadic ones. And the sporadic ones you can think of all as based on these kind of, I call them, the Platonic solids and the analogous things on the projective plane. These sort of maps that are vertex and edge and face transitive on the surfaces of positive Euler characteristic, the sphere and the projective plane. So this is long. It's got an induction that's way more complicated than that proof by contradiction before, and there are a lot of technical lemmas. But there are a couple of ideas that I can communicate quickly here that are really central to it. There are 2 on this page. Let's do the top one. One is, suppose I've given you, I have this structure here, this sort of tripartite graph, and a group that's acting on it in a very nice way, that's transitive on each of these blocks. Well, in fact, this is kind of an overdefined structure. You don't really need all this information. You could actually just reconstruct it from here. So what's the idea? Well, if if I told you just how the group is acting, and I told you just the neighbors of this one vertex x, so I tell you who it's joined to over here and who it's joined to over here, you could then reconstruct the whole, because you apply your group action to it. You say, you apply your group action, that's going to map this pair of sets to some new place. Well, that new place is, say, g times x. Right? I could figure out what all of these incidences are if I just know how the group acts and I know just two of these sets. So I can kind of reconstruct the picture from here. The other key thing I can do is actually the same sort of intersection union trick. So that same technique that we saw working to get a handle on these small product sets, we can still use on the setting of these graphs. So the idea is you take two vertices here in the same block, and what you're going to do is you're going to look at their intersection over here and their union here. That defines something that looks like this. That I now have a one block over here and one block over here, and a new set on the left and a new set on the right. I can then reconstruct one of these whole triples from that. So I have a way of doing a kind of intersection union argument that's very similar to what we saw before, but now it's operating on graphs instead of on groups, and that's kind of the key thing that sort of gets me started. And so the way the proof goes here is that you work with these structures and you have this kind of operation of somehow taking a structure and maybe making it a little bit more extreme. And I'm like working at great length to kind of classify these structures. Once you've classified these structures, then in order to know what's happening with those product sets, you have to back up and ask how the groups how groups can act on these structures. But that question tends to be fairly simple, because mainly because the things I get are sort of like cyclic or dihedral. So another kind of advantage of this approach is by first classifying the graphs and then doing the groups, you find that the same structure leads to multiple groups. Like that exceptional structure of the cube that we saw actually leads to exceptional product sets in 3 different groups. Because you've got sort of the whole symmetry group of the cube, which is the rotational group S4 cross the central inversion, the map that maps everybody to their antipode. So you've got S4 cross Z2, and you've got S4, and you've got an A4 cross Z2 still. So this sort of this one structure gives you many different product sets. Anyway, so as I say, I mean, this is just some sort of hint of what's going on, but I think it's the best I can do. And so I will stop there. Thanks for your attention.